You're doing great. So in this video, I'm going to actually talk about something that has been really been a lot of interest to me. I have been finding it very interesting over the last year or so, but in particular, the last few months, I've been exploring something called causal inference. So those who are from econometrics backgrounds or from more statistics related backgrounds, they are probably aware of it, but it's still not quite in the mainstream in the industry, except for a few places like, say, biostatistics or medical research. um, so this is all about the science of what causes something. And while it may sound very simple, it's actually easier said than done, because what is the real cause behind an outcome is something that actually depends on a lot of factors, and we generally don't have availability of those factors, but we sort of overlook the fact that there can be other things that can be called as confounders, as we'll just discover. So I'm going to also bring this in the context of performance marketing. I'm going to discuss it completely in the performance marketing context, because obviously that's my target audience. You people are in marketing, and so I want to show you why this is important. So, as you can see, the title of this discussion today is causation, confounding, and counterfactual. So, I'm going to introduce these three terms, and I'm going to also talk about why attribution alone, therefore, and attribution in any way, really, the regular ways in which we attribute credit, assign credit to different kinds of channels or campaigns. So let's actually move forward. So, what is our goal really? We want to understand the causal impact. So, this really starts from an understanding that correlation is not necessarily equal to causation. So, we may see that two channels, or rather two variables, suppose the ad spend from a channel and the sales, overall sales, they are very strongly correlated. So correlation is measured by Spearman's coefficient, or there are other simple measures, just by a small Excel command or a small piece of code in Python. You can actually measure correlation very easily, but the problem is that's not going to give you a proper causal effect. Why? We're just going to come to that. So today I want to show you a couple of short Python simulations, but the code is not important. It's going to be the analysis and the outcome coming from the code that we will really be interested in, and we'll try to connect that to incrementality. So you want to understand the effect of exposure on an outcome. So it's not correlation but incremental lift. That is what we are truly trying to understand. So if we move on to the next slide, we are talking about the fundamental problem of causal inference. So let's take a step back now. So we are trying to understand the incremental lift. Okay, so if something is happening, like if there is an impetus or an input, like suppose an exposure, an ad exposure, suppose it's a campaign that's running, so we want to measure the lift, right? So what we are effectively trying to understand, essentially we're trying to understand if if the ad had not been there, what would have happened. And of course we have also the observed effect of what has happened after the exposure has been really there. So the difference between these two cases, really, that is what we are trying to measure as incrementality. And that truly, if it is measured properly, that will give us a causal effect. So there's a very close correlation, no pun intended here, but there is a very strong correlation between the concepts of causality and incrementality. So I have heard this question before, or this doubts, like, does incremental analysis truly give causality? Yes, if you're following the proper approaches of causal inference methods. So this graph here, and I'll come to the equations in a bit, this graph here is showing that thing precisely. So you have, suppose, something that was going on for a while, like you have sales, and now you have this blue dotted line, right? Over time, say this x-axis can be say time, and I've deliberately removed the variables from x and y because this could be anything, but this is more or less time, and this is basically your sales or any target variable in the y-axis. So this blue dotted line here, that represents your intervention. So something has happened, like this is an ad exposure, this is a new campaign that you've launched, this is a new discount or a promotion, it could be anything. So what is happening here, you'll see that it is now getting split into two lines, the blue line and the black line. The black line is the one that's observed, so that's a true observed thing. That's what's happened after the ad exposure has been there, and you can see that there's actually an upward shift towards the um, you know upward basically after this intervention. And the counterfactual, this word here, counterfactual, and this is important, counterfactual thinking. What would have happened if this had not even taken place, this intervention? That's what is represented by this blue line. So this is what would have happened, and this is basically something, think of it, which will actually never know for real, right? So we will have to estimate this, because obviously we don't know what would have happened if something that has happened in reality hadn't happened. I know that's a mouthful, but this is what we are trying to get to essentially. And the problem is that marketers are not trained to think like this. We are always trained to think always in the heat of the moment, like we are always in the present. But we have to step back sometimes, take a couple of steps back and start thinking in this sort of fashion. This is a very, almost a philosophical way of thinking, but fortunately for us, we do have a lot of nice quantitative, mathematical, and technical tools to actually make this work. So we can estimate this counterfactual, and this starts all from this statistical representation of the problem here. The fundamental problem, as we say, the fundamental problem therefore is that we never know that the counterfact, we can never truly know the counterfactual, we can only estimate it. And we have to estimate it if we have to get to our ground truth of understanding incremental lift. So what is the individual effect? The individual effect is that effect of the observed, so the effect of the intervention and the observed value minus that counterfactual. So the counterfactual is basically the situation, the outcome when that input was not there. So one represents the input being there, and zero represents not being there. It's a binary. So we can only observe one of these two, right? So either you are going to give that impetus or you're not going to give it, right? So if you're going to give it, you can only observe yi of 1. I represents multiple units, right? I mean, you can ignore it for this purpose. These are all coming from very mathematical expressions, but I just want you to understand the point here and appreciate the requirement of such an analysis. So yi0 here, that represents your counterfactual, okay? Because that is basically something that has not been observed. So the difference between these two, this little space here between these two, which can be mathematically computed as well, either through code or otherwise, this basically represents, and this of course, as you can see, this is also going to change over time, right? As the difference between these two grow, or they converge, whatever happens, this is basically going to give you the distribution over time of the difference between the observed and the counterfactual, which is your lift. And this becomes a causal impact analysis. This gives you the true causal effect if you are following certain practices, by the way. So there are certain assumptions, there are certain sort of prerequisites for these kind of tests to be, incrementality tests, to actually give you causality. So incrementality tests, yes, per se, they're not causal tests, all right, or they don't give you the causal impact. But to truly understand causal impact, incrementality tests can be conducted in scientific ways with scientific setups that can give you the causal impact. Now let's move on to the next one. So we are talking about confounding. Why is this entirely happening? Why does it complicate matters so much? This is mostly happening because of confounders. Okay, and confounders are nothing but another variable that we didn't actually take into account in our analysis. And as you can see here, so we typically look at these, so multiple independent variables. This is just one for representation purposes, but you can think of it as multiple independent variables which are related to dependent variables, right? Now the thing is that you might have another variable or multiple other variables which are related to both the independent as well as the dependent variables. Okay, so basically you can think of this as the treatment and this is the outcome. So anything that is related or associated with both treatment and outcome, that's basically your confounder. And we often are not able to analyze this properly, which is what leads to all kinds of problems like selection bias, as we'll just see. So this is basically also something that leads to what's called the omitted variable bias, or the OVB. And this is very common, by the way, in marketing, and we'll just come to an example in a moment as to what kind of examples that are there. In fact, I can just point it out right now. A great example of that is just the case we were talking about. Like, we try to understand from a performance marketing point of view. We see that suppose during Black Friday, or suppose during some other part of the year, like when there's a major event, we are looking at ad spends and we are trying to measure MER, for instance, right? We are trying to understand MER or say AMER. We're trying to understand, we had the total revenue, or we had the total, or maybe you can have even POS, blended POS. We had contribution margin or gross profit, and then you divide it by the total spend across the channels, and you see a lift there, just in this form of naive division. And you see that, okay, great, if it's increasing, then that's a great thing. The problem there is that you are actually falling prey, quite potentially, to the omitted variable bias, because you're not considering the fact, for instance, that during a special season there's going to be a lift anyway, right? There's going to be more demand, there's going to be a greater conversion rate. So you have to take that into consideration, and unless you do that, you're never going to be spending money incrementally, like, or you're also not going to be able to truly understand the causal impact of every additional dollar. So I hope you're able to appreciate now from this from this discussion, the close relation and association between incrementality and causality. Now this here, the side that you're seeing, this is a little mathematical, but this is very simple regression, linear regression only. But this is at the heart of causal inference. What is the data generating process? How does the data get generated? That is what we really want to know. We will never know this for absolute fact. So what I'm trying to say is, suppose you've got X amount of sales in a certain period of time. What are all the things that have actually led to that, and how are they all related to each other? That's the question that I'm trying to answer. That's the question that this slide is asking. What is the data generating process? Nobody knows. That's happening, right? I mean, that's just happening. Some of it is because of direct intervention, like for instance your ad spend, like customers just taking more interest in it. But then there are other external factors like economic or macroeconomic factors, political climate, social factors, lots of things, behavioral changes. A lot of these are happening in the moment. A lot of these are sort of slow decaying, or sort of continual effects. So that's a massive task, and honestly speaking, I don't think that will ever be fully understood, but you can estimate them statistically. And that's the whole point of this, the data generating process. As long as we have a very good idea about that, we can get very close to the proper ground truth, and therefore the causal impact of different interventions. So this is what is called simple DAGs, or directed acrylic graphs. I'll probably talk about it later on as well, and you can already start looking at things if you want to, but these are very simple relationships that you can assign. So what we have here, in what you in front of you, you have a confounding variable u, and we have the dependent variable y and the independent variable x. So the confounding variable, as you can see, it is affecting both x and y, and x is of course affecting y. So these are the set of three relationships that are defining the regression that we're going to do. So we're going to do two models. The first one, so u here is simply a normal distribution with mean 0 and 1 as standard deviation, and your x and y are also related in this, as you can see. So x is dependent on u in a certain way, with just a simple constant as intercept, and then an error term. And then you also have the y, which is also dependent on both x and u. And you see that we are fitting two models, two simple linear regression models. So one is omitting u, another is adjusting for u here. So it's directly related to x, and this is directly correlate regressed with x and u, just additive. So very simple linear regressions. This is what I've done through a Python simulation, and this is the output that I've got from here. So the output here, so the first case, so this is by the way true. So what we are trying to do here, why the simulation at all? This is just to show you that when you know the data generating process, you can actually know whether or not a certain regression process or a certain regression method or a certain, so basically think of regression, if you're not very familiar with regression, it's nothing but a statistical approach, a mathematical approach to understand what is causing the outcome, what are the variables and how they are related to each other. So you see that these are the two models, right? The two estimates that we're getting from the two models that we just saw here. The first one which accounted for the confounding variable, and the second one which didn't. And we see the difference in the estimates. So this is the true estimate, and we saw the second one, since since it was such a simple regression equation, and since we took u into account in the second one, the second estimate from the second model is actually so close to the true value, right? It's actually almost equal. The first one, though, missed the mark by quite a bit. It overestimated, right? So it overestimated the effect of X because it did not take into account U. Now, get back to a performance marketing example. This is exactly what I was talking about. If you have um so if you are suppose doing this analysis for suppose the Black Friday or any other special event of the year, and you're only taking into account suppose ad spends or maybe organic channels, and maybe a couple of other variables typically what marketers will look at, and many of them of course not doing regression analysis at all. That's kind of close to mmm. But even in the naive sort of analysis, they're omitting variables all the time. um, Either they if either because they're not aware of them, or simply because it's just going to complicate things too much. But if you do that, you are potentially going to overestimate the effect of the independent variables or the treatment variables on the outcome. And that's exactly what has been shown here through this bar graph, that when you take all the variables into account, you're much more probable, it's much more much more, the chances are higher for that estimate to be closer to the ground truth. So I'll quickly jump into the Python code now as the last step of this discussion. So this is what has been generating. So as you can see there, we have the unmeasured confounder, which is the u, the x and y. We just showed that. So this is the random variable here that's basically doing what it's supposed to do, generating some values for the regression equation. And we fit this linear regression model. We have two models, as you can see, OLS models, ordinary least squares, and we are adding that constant term, and we are fitting these models, one with u, another without u. As you can see, this one has u, this one doesn't have the u. And then we are going to do the simulations for different values. And this means that we are going to be able to get different values of the coefficients as well, and finally the estimates. So these are the estimates. So as you can see, the true value was 1. Okay, because we did have the data generating process in this case, right? So this is not going to be there in reality, but this is just to show how this works behind the scenes. So we knew the data generating process, and from there we knew that the true value of the estimate should be 1. And we see that the second one, the case where we actually did include u, this one here, that estimate is far closer to 1. It's just off by 0.001. This one is off by quite a bit, almost 50%, maybe, like it's 1.4 or 40%, 1.4, as opposed to the true value of 1. So if you actually plot this is the plot that I already showed you, which shows the differentials in the estimates depending on what model you have got. So the two main problems here, so we can't observe counterfactuals, and then the simulations let us cheat and know the truth, right? So that's what we are doing. So we are trying to simulate, and we are basically trying to see what's closer to the ground truth. So the omitted variable bias, crept into this case here in this estimate one, because we did not take into account the omitted variable u. And we are going to do another quick plotting here, and this is going to show us the distribution for different estimated coefficients. So this is basically, the distribution is a result of different simulations of the different coefficients. Okay, so we are changing the different values of the coefficients that we initially had in the data generating process. Okay, so we had the coefficients, so for instance zero point 0.5 here. So we are going to do different simulations of the same, and then we're going to see what we can do to what that actually does to our overall estimation. So we see that in the first model itself, we see that it's very much centered around 1. So this is possibly the median and the mean both, because this is a fairly normal distribution, and you can see that the line is passing through 1. So that's close to the estimate, right? That's close to the ground truth. So the estimate here is very close to the ground truth. In the second case, even with all the simulations, you can see that it's more or less centered around 1.4, as we saw earlier, right? So this is what the visualization is showing. Like for one, the estimates without adjusting for the confounder, the estimates while adjusting for the confounder. and the histogram is centered around one, the true effect. It shows that when you control for the confounder, the estimate is unbiased. You recover the correct relationship between x and y. So that's what's happening here. This is an incredibly interesting thing if you think about it. You are genuinely uncovering. Think of the power if you could really do it. But it probably won't be ever possible because we won't truly know the correct relationship between, say, ad spend and all the important variables. But if you are omitting an important variable, right, in your understanding of what is really causing an impact, suppose the sales peak during Black Friday, you are going to suffer from the omitted, your analysis rather is going to suffer from the omitted variable bias. So that's pretty much what I wanted to show here, and this is an introductory analysis. So what can you do? What is the takeaway from this? You can definitely, and you should definitely, do incrementality tests. Okay, so incrementality tests are going to be, are absolutely the gold standard in this case. And they definitely, if you are following all the best practices of causal inference methods. So causal inference is at the heart of it. That's what I just wanted to show, how it is closely linked to the concept of ground truth. You can literally recover reality if done properly. Um, so yeah, I mean, incrementality tests, if done following the processes of causal inference methods, there are so many out there. I've discussed a few already. I'll keep showing more and more results. I do this in practice a lot in my performance marketing analytics work, in marketing analytics. So you can use DID, or difference in difference. You can use causal impact packages that are there as well. These are Python libraries, so you can do a lot with that sort of a thing. And you can use synthetic controls if you're doing geolift experiments. You can use propensity scoring. So a lot of methods are there. Different methods are useful and relevant in different situations, so that has to be taken into consideration. But this is the broad direction that I wanted to give you, so that you get motivated to start thinking from the point of view of causality, and take into account things like, say, counterfactual and confounding. In fact, this entire process, by and large, is called causal thinking and counterfactual thinking. So that's what I really want to sort of motivate marketers to take up as an initiative. So hope this was not too heavy, and if you have any questions, I'm absolutely happy to clear out the doubts. Do leave your questions in the comments, and thanks for watching. I'll see you in the next one.